Great. For our second presentation, we visit Israel to hear from Eran Inbar, CEO and founder of Prisma Photonics. Eran holds a PhD in lasers, physical electronics, from Tel Aviv University, with many patents relating to novel laser design. He was the CEO and founder of VGen, among the early and dominant players in the fiber laser field. VGen was acquired by Newport Spectrophysics in 2014. Since 2017, Eran is the founder and CEO of Prisma Photonics, focusing on smart physical infrastructure based on novel fiber sensing technology. Over the recent years, Prisma Photonics has won multiple industry awards and successfully demonstrated and deployed its unique solutions in the pipeline, power, communications, and other infrastructure fields. Eran will present novel classification of leak detection and third-party intrusion, enabling best-in-class false alarm rate. The floor is yours, Eran.
Danny, thank you very much for the kind introduction. In this presentation, we will discuss and present fiber sensing for oil and gas pipeline, and the focus would be driver to achieve best-in-class false alarm rate. Before diving into the technical details, just a brief about Prisma Photonics. So the company was founded 3 years ago, and our sole and exclusive focus is next generation fiber sensor for smart infrastructure. And if you would ask what is the next generation or what is the difference between first and second generation, I think that this presentation will give the insight about it. We will also present in this presentation our Hyperscan technology and why it's crucial in order to achieve robust and reliable detection. Our main focus is smart infrastructure, and oil and gas pipeline is one of the main market segments. But just to give a high level, we're also covering electrical grid monitoring, perimeter and border control, railways, physical cybersecurity, smart roads, and subsea. To give a high level concept about what is fiber sensing for anyone who is not familiar with, so instead of spreading multi-thousands of sensors along the pipeline, the idea is to use standard optical communication fiber. It can be even a pre-existing telecom fiber. And just by plugging the system into this fiber, a single system can turn 100 kilometers of optical fiber into a sensor. So the overall setup it's a very clean architecture, very simple. So we have a pipeline. Along the pipeline, there is a fiber. And every 100 kilometers, we have a system. Everything is injected into single and consolidated user interface. What can be detected using this technology? So it can be anything from, of course, leakage detection, inline pigging devices, intrusion like theft, vandalism, third-party interference, and also mechanical, manual digging, pedestrian and vehicle movements. And it's important to emphasize that with this technology, you get a precise location of the event in a resolution of a few meters. That's part of the inherent capability of this technology. I spoke about detection, but I think what is even more interesting to speak is about classification. The idea is not only to detect an event, but classified between the different type of events. And I would go into details about this aspect later on in this presentation. So let's speak about the challenge. So when we're using fiber sensing for pipeline monitoring, what we're trying to do is basically attempting to detect very rare events. So leakage or third-party interference, it's something that can happen once every few months even. And we are doing it in a very noisy environment. So we can have other events, non-relevant events that can happen thousands, 10,000s, or even more than 100,000 events per day. So the key to reduce the false and the nuisance alarm is a matter of classification rather than detection. How can I classify between the few events that are relevant for me and between the many other events which are completely not relevant for me? And the solution that we will present is our unique and proprietary Hyperscan technology. And we will show how by generating very clean data with very high signal to noise ratio, with generating a lot of details and features in the data, we can achieve very high level of classification. I think the best would be to start with an example. And what we're seeing here is a typical DAS picture. DAS, it's distributed acoustic sensing, which is the common method for fiber sensing for pipeline monitoring. This picture is called waterfall. The y-axis is the time, and the x-axis is the location along the fiber. And in this picture, there is an event. There is 4 human footsteps. And I will encourage you to try to find those 4 footsteps in the picture. And I would guess that most of the people would say that this is in this bright line, the footsteps. But this bright line is basically a very strong background noise, and it's completely not correlated to the footsteps. Let's look at the same scenario with our Hyperscan technology. And here, clearly we can see the 4 footsteps. So in the typical DAS, it's very, very hard to see them because they are 30 meters away from the fiber. It's a weak signal. But with the Hyperscan, you not only can detect them, but you can know a lot about them. You can see the acoustical signature. You can know the signal strength, the cadence of the steps, the distance between the steps. So you can gather a lot of feature about it that would help you to do classification. If we're trying to look at the same scenario that I showed in previous slide with other state-of-the-art fiber sensing technologies, phase-sensitive PHY-OTDR. Take a look at the left image, the typical DAS in a phase map. You see that it's very, very noisy. It's very hard to see any image. If we're looking at what is today seems to be best in class, seismic grade fiber sensing system, they are complicated, complex, and expensive, and very rarely being used for pipeline monitoring. Even with those systems, it's very hard to see anything. If we're looking at the Hyperscan, we can see those 4 steps in a very high contrast with a lot of features. Let's go to another challenging classification problem, which is, can we classify between a human and an animal? Here you can see human footsteps on the left. You can see the image, the picture of the steps. And here are 3 examples for different animals. This is the picture of the steps of a fox, of a horse, and of a boar. So even without knowing a lot about the technology, you can see that the signature and the characterization are very different in between each one of the pictures, and you can probably guess that those pictures are well suited for machine learning based algorithms. How it's working, how the algorithm is working, and this is a complicated slide, and I would try to simplify it. And I would simplify it into a single word. And the single word is storytelling. We would like to tell the story behind the event. And that will help us to reduce the false alarm rate. So data is streaming, and we have multiple detectors that are trying to detect multiple features from the data. Based on those multiple features, we will build events, and we will classify those events. But classifying the event, it's not enough to get low false alarm rate. We need the alarm is basically a cluster of events. So we're collecting a lot of events and trying to understand what is the story. If we're speaking about the footsteps, we will try to understand the single strength, what is the distance between each steps, what is the speed, what is the cadence, what is the direction, and try to see if it's correlate to the target that we are looking for. That would allow us to go into a negligible level of false alarm rate. Let's go to another example, which is classification of both mechanical and manual digging. Digging is a very high risk for pipeline, both for tapping or accidental damages. In the upper image, what we can see is a mechanical digger, and in the other side, we can see the signature of a water pipeline. They can, one can mistake and misclassify in between them, but if you look at the high quality data, like the data we're presenting, you can see that that look differently, that allow us to basically classify and know which one is the digger, which one is the pump. Another example in the bottom picture is the difference between very weak signal to very strong signal. We have a very weak signal, which is manual digging. We have a very strong signal, which is a construction site very far from the fiber. The construction site, even though it's very strong signal, it's not really relevant. So if we deep dive into the data of the manual digging, we can see each heat hole and each heat hole, and we can understand the rhythm, we can understand the process, and we can basically tell the story and understand if it's some kind of background noise or is it an activity that we're looking to detect. Let's deep dive into this storytelling, and let's take a look at mechanical digging. And here I'm giving a sample of 20 seconds of mechanical digging, and you can see in the Hyperscan image very clear 2 hits on the ground. I would say that there are strong hits, and even in a typical dust, you can see definitely the first one and maybe even the second one. If those will be the only feature that would guide us to take a decision, we will have a very high false alarm, because you can find a lot of strong events. Now we're trying to tell the story. Now we will try to take a look and see what's happening immediately after the digging. So immediately after the digging, what we're seeing is the scrape of the digger on the ground, and right after the scrape, we can see the frequency of the motor of the digger. So we have here a story, a hit in the ground, a scrape in the ground, a motor. We know for sure that this is a digger. If we try to see the equivalent in a typical dust, it will be very hard to get the fine-tuning of the scrape and the motor, and we will not be able to tell the story and get a very low false alarm rate. Another aspect that we would like to speak about and emphasize, it's the number of events or irrelevant events that you may find along a pipeline. So this is a real measurement, 35 kilometers of a gas transmission pipeline. And this is just 1 second measurement, a measurement over 1 second. And you can see that in 1 second, there is close to 10 events in 1 second. And it's caused by, because in some cases, the pipeline is close to a highway. In some cases, it's close to a city. There is construction site. There are agricultural fields. If we will take this data and accumulate it over 24 hours, we would reach into almost 100,000 events. After classify them, we find out that there is 0 alert, 0 digger, 0 real event. But just understand the ratio between a real event that can happen once every few weeks or few months, into events which are not relevant. There are real events, but not relevant for us, that can be up to 100,000 per day. The last example that I would like to give is a leak detection. So if we're measuring a leak from a pipeline, we can see that the leak generates a very strong signal. It's definitely, you can detect it. But the problem is that such a signal is a signal that can be generated by many other targets. Most of them are not relevant for you. So if you would try to detect it based on this information, you probably reach very high false alarm rate. So one of the ways to tell the story and analyze it is to look at the frequency content of this event. You know, it's like an analogy, it's like what Shazam is doing in the music application. So now we're looking at the frequency range, and we're seeing a very clear frequency signature. We can see where the leak starts, when it ends, what is the frequency content. And this is, just to give and emphasize, this is a 7,000 standard liter per minute, which is something like 0.1%, relatively a very low leak, but still a very, very defined and well characterized. We can go into 200 SLPM. This is very, very weak leak. This is 0.02%, and still we can have a very clear frequency signature of those leaks, which allow us not only to detect, but detect with a very low false alarm rate. So to summarize, pipeline monitoring, it's not a detection, a simple detection event. We are trying to detect very rare events that can happen every few weeks or every few months in a very noisy environment that can generate something like 100,000 events per day. This is basically the main mechanism for seeing in those systems relatively high false and nuisance alarm rate. What we present is novel and proprietary technology called Hyperscan fiber sensing, in which by generating very high signal-to-noise ratio signals with ultra-rich features, we can do a very advanced classification capabilities that those are the keys for us to reduce the false and nuisance alarm to the minimum. Thank you very much.
Thank you, Eran. I like that, especially the detective work, and it's clear that there's scope for machine learning to look at the signatures there. Let's start with some questions. I have one from Cyril Babal here, who asks, can you share some experience of how you would install this on a pre-existing pipeline?
Yeah, so basically you have two scenarios. One of them, all pipeline without fiber sense, without fibers. Therefore, you're required to install the fiber. I think that the interesting aspect is many pipeline have along the pipeline optical communication fiber that were installed for communication, not for sensing purposes. They are not very, very close to the pipeline. They are in conduit that attenuate the signal, but they are there and you can use them. And that's why this is another aspect that I didn't mention in the presentation, that you need very sensitive system, because if you would like to use those fibers, and if you can use pre-existing fiber, the cost and complexity would be significantly reduced, so you can use them and basically ramp up immediately. You don't need to install anything.
Thank you. That leads me on to another question from Louis Capirua, who asks, does the positioning of the fiber optic cable matter? I guess you've explained that it can be even far away from the pipe.
Yeah, so there is a dependence for many aspects. The distance from the fiber, the location from the pipeline, the location, is it above, below, close to the pipeline? What type of cable do you have? Is it in conduit or not? All of them have an impact. And when you're building your database, when you're building your algorithms, you must do the test and test all those scenarios and have a rich database. If you would test single scenarios, one location, one cable type, one installation type, it's, you don't have any guarantee that you will be able to detect in high probability in different installation. So this is a good question. This is key here. You need to collect a lot of data. It's a hassle, but it's part of the game.
Makes sense. We have an anonymous question about damage to the cable. Is the cable susceptible to damage, particularly in more than one place?
Yes. So, as all telecom companies would tell you, from time to time, people are cutting by mistake, usually construction side, they're cutting the cable. What's interesting in this method, that if the cable is being cut, we would give an exact location in a resolution of meters where the cut is, so you can easily come and connect it by, do fiber fusion, and the system would work 100% from your system until the fiber cut. So you still have the system working on this, and you know exactly where the cut is.
Makes sense. That leads on to another question from one of our panelists from earlier, Ben Adebayo. He asks, is there a way to install future pipelines with an internal fiber optic strip so that it doesn't interfere with pigging, but is protected?
Yeah. So there is a lot of benefit about thinking about how we can attach the pipeline and the fiber together and increase the sensitivity. So definitely there is a place for it. Our approach as Prisma Photonics is saying we have like 4 million kilometers of installed pipeline. Many of them have telecom fiber along it, not in an ideal situation, but they are there. And if you can bring a reliable solution for it, you have a huge market. You are not just speaking about, the future installation, the next project. You have a huge market waiting for you. So that's our main focus. Definitely there is a place for someone developing system based on unique attachment of fiber to pipeline.
Thank you. And one final question, Eran. Can this technology and technique be used for monitoring near-miss events to avoid incidents or accidents?
What kind, sorry?
To monitor near-miss events to prevent incidents or accidents happening.
Yeah, so you're speaking about, not about pipeline monitoring?
Yeah, I mean, for instance, there could be a situation where a dig nearly hits a pipe, and then you can use that to then prevent that from happening in future.
Yeah, so definitely what in this technology, any kind of digging, even tens meters away from the fiber, since it's a big event, would be detected, localized, classified. So any kind of events, even the one that are not hitting the pipe, would be detected. We can know that there is a digging, and we also can know when the digging is hitting the pipeline, because there is a very clear acoustical impact for this aspect. So we can, for example, let you know what is the statistics of digging around your pipeline, even though no damage happened. So you know if you are in a high risk or low risk environment.
Perfect. Thank you very much for the presentation, Eran.
Danny, thank you very much.